motion is based on the law of conservation of linear momentum. The interesting aspect of the rocket motion is that the mass of the system changes during the motion. The rocket vehicle has a chamber in which the fuel, which can be a solid or liquid, is oxidized and burned. The large quantity of heat of combustion produced rises the pressure inside the chamber, resulting in the burnt of gases issuing out of an orifice at the tail end of the rocket in the form of high velocity steam called the jet. A rocket fired from the earth will always be affected by the gravitational pull of the earth, but let us neglect it to simplify the problem. Consider a rocket whose vehicle mass is mv and let the initial mass of the fuel in it be mf. So here we can write the initial mass of the vehicle is mv and mass of fuel is mf. Then the initial mass of the rocket. Then the initial mass of rocket is m naught is equal to mf plus mv. This is the equation number 1. Let m be the mass of the rocket. Here we can write let m be the mass of rocket and v is its speed at any instant of time observed from the earth. Let the rocket, here we can consider that the rocket move in x direction. Here we will draw the diagram. This is the fuel part, m mass of the rocket and the direction in which the rocket move, whose velocity v at a time t is move in a x direction. Finally, when a fuel is burned whose mass is delta m, and if we have to see from the earth, its velocity is u minus v, and the remaining jet whose mass is m minus delta m, and the final velocity at t time t plus delta t is velocity e plus delta v is at after some time. Let delta m be the lost by the rocket in time delta t due to the burning of the fuel and expulsion of an equal amount of mass. Here this u minus v is the velocity of the exhaust gases. So we can write u is called exhaust velocity. Exhaust velocity. So here at time t we can find out the linear momentum. At time t the linear momentum of the system is mv, and at time after some time t plus delta t the linear momentum of the system is, we can write here, m minus delta m multiply by this v plus delta v minus of delta m multiplied by this u minus v. So according to the law of conservation of linear momentum, according to the law of conservation of momentum, is, we can write here, mv is equal to m minus delta m multiply by v plus delta v minus delta m multiply by u minus v. We can write here multiplication, multiply that mv plus m into delta v minus of this delta m into v plus delta v plus u minus of this term. So from this equation we can write here m delta v is equal to u into this delta m, here neglecting the delta v. Okay, comparison to the initial velocity u. So we can divide by, if we take the after some time delta t dt, we can write here delta v upon dt is equal to u into delta m divided by dt. So here, but here this delta v upon delta t is nothing but it is the acceleration of the rocket, and this delta m upon delta t is equal to, we can write, minus dm upon dt, minus dm upon dt. This negative sign indicates that m mass is decreases with increase in time t. So here we can write m into dv upon dt is equal to minus u dm upon dt. So we can write this dv upon dt is nothing but acceleration is equal to minus u dm upon dt. This equation is called as the equation of motion of rocket. Okay friends, if you up to this point you have to understand that the how we can determine the equation of the rocket. So the RHS term of this equation of motion of the rocket is the rocket thrust. So we will determine this value and substitute into this equation. Okay, so we have to take the thrust is equal to minus u dm upon dt, and by integrating this equation v0 to v dv is equal to minus u m naught to m integration of dm upon m. Here m naught is the initial mass and the initial velocity of the rocket system is v0. So here v minus v0 is equal to minus u natural logarithm of m upon m naught. So we can write this equation as v is equal to v naught minus u natural log of m upon m naught. Let when this fuel is burnt, then what happens? Let this fuel burn at a constant rate and t be the time for which it lasts. So we can write at time t is equal to 0, the mass of fuel is mf, and at time t is equal to capital T, at that time the mass of fuel is totally burned. So we can write it is equal to 0. So here we can see the time between t is equal to 0 and t is equal to t. So we can write that at time t between 0 and t, the mass of the fuel burn is equal to small t upon capital T multiplied by the mass of the fuel. So therefore we can write here m is equal to m naught minus t upon capital T multiplied by mf, for t is lies between 0 to capital T, and when mass m is equal to mv at this is the constant mass for time t is greater than capital T. So from above equation, this one we can write m upon m naught is equal to 1 minus T upon capital T multiply by mf upon m naught. So substitute this m upon m naught in the first equation, that is this one, in the star equation. So the above equation becomes as here V is equal to V naught minus u of natural log of 1 minus T upon capital T multiplied by mf upon f naught. This is the equation number. So now see how that rocket attains the maximum velocity at time t. So you will see here what I said here. A rocket attains maximum velocity at time t when all the fuel is burned up. So we can write the maximum velocity of that rocket is Vmax is equal to V0 minus u into natural log of 1 minus mf upon m naught. So this T is equal to capital T. Okay. After that, so this maximum velocity is, we can write here V0 plus u into natural log of 1 minus mf upon mv. This above equation shows that the larger value of the mf upon mv 1 plus. If this value or this term is maximum, then there will be a maximum velocity. So we will find out the position of the rocket at any instant of time t. We write V is equal to dx upon dt in above equation. Therefore we can write x0 to x dx is equal to 0 to t into V0 of dt minus of u into 0 to t ln of 1 minus T upon capital T into mf upon m0 multiply by dt, or we can write as a x is equal to x0 plus v0t minus u into I. So x0 is the initial position of the rocket. We can write as a, here it is the initial position of a rocket. So we can integrate this equation. Okay, so we'll see here what will be the value of that integration may arises. So here we can write that integral term is I ln of 1 minus small t upon capital T multiplied by mf upon m naught into dt. Let we can here substitute, that is 1 minus mf upon m naught multiplied by small t upon capital T is equal to y. Then minus mf upon m naught into t dt is equal to dy. We can take the differentiation. So here the I is equal to, that value starts from 1 to 1 minus mf upon m naught into small t upon capital T minus this term mf upon m naught t into ln of y dy. Therefore, to solve this integration, so the term becomes as so here we can write this equation as a 1 to 1 minus mft upon m naught, take the integration, that is m naught t upon mf into ln of y into dy. Therefore, by solving that equation, integration, it becomes as y of ln y minus y, whose values limits are 1 to 1 minus mf of small t divided by m naught. Then substitute that value, m naught t upon mf is equal to 1 minus mf t upon m naught t into natural log of 1 minus mf t upon m naught t in minus 1 minus mf t upon m naught t plus 1. So the value becomes as, if we can multiply here, so minus m naught t upon mf minus gets cancelled, mf gets cancelled, so the terms becomes as a minus m naught t upon mf plus t. We can write as a t minus m naught t divided by mf into ln of, this will becomes cancel, so the terms becomes as 1 minus mf t divided by m naught t minus of t. So we can substitute the value of this integration in above equation. Therefore the x displacement, or we can say that position of the rocket is x is equal to x0 plus v naught t minus u of this term, that is t minus m naught t upon mf into natural log of 1 minus mf t divided by m naught t minus t. So this is the solution of equation of 1, and this gives the position of rocket at any instant of time. Thank you very much for listening this video.